Welcome to our very short discussion about Venn diagrams. All right, let's start off with an example. So we want to use the following Venn diagram with two overlapping circles. The reason why we point that out is sometimes Venn diagrams can have more than two circles. You can have three and even more. And we want to shade the regions that represent the given sets. So you can see that the kind of peach color is set A, and the green color is set B, and then that dark football in the middle, that's where those two sets overlap. So the first thing is they want us to take the complement of A and intersect that with B. Well, remember, the complement of A is everything that isn't in A but is in our universe, right? So excuse me, I didn't learn how to color inside the lines in kindergarten very well, but you get the idea, right? This, everything out here is the complement of A, including this stuff that's in B because it just can't be in A. All right, so all that yellow stuff is the complement of A. And then B, of course, right, is all of this stuff. And they want the complement of A intersected with B. So what do those two things have in common, right? What is both yellow and has red stripes? And you can see that it's colored down here in blue. It's this kind of, looks like a cookie with a bite taken out of it, and it's just got the number 4 in it, right? So the complement of A contained 4 and 1, because those are the only things out here in this set are these four numbers. And then B contained 4 and 3. So if you want to think of it, as far as numbers are concerned instead of pictures, the complement of A had 4 and 1 in it. And then, of course, B has 4 and 3 in it. And the intersection says take what those two things have in common. So the intersection, the only element those have in common is 4. And that's why we end up with 4. All right, how about another one? Now we're going to look at the union of the complement of A and the complement of B. Well, the complement of A is everything that isn't in A, including, right, this part of B. Then the complement of B is everything that isn't in B, including that part of A. And then the union, right, is everything that is in one or the other or both. So basically anything that either has red stripes or green stripes on it. And so it's going to be everything but that little football shape in the middle, right? This little shape here in the middle is the only thing that didn't have red and green. I mean, there's a little bit on it just because I can't draw, right? But you get the idea, right? So down here, we've shaded everything but that 3. And again, if we wanted to, we could list out the sets, right? A complement, remember, is everything that isn't in A, so that's 1 and 4. B complement is everything that isn't in B, so B, right, you can see it better down here, B's got 4 and 3 in it, so that's 1 and 2. And so the union is you basically take these two sets and add them together, so everything that's in both, so 1, 2, and 4. And you might ask yourself, well, how come you don't list 1 twice? Well, because you never list an element twice. 1 is in the set. Putting another 1 in there just says that 1 is in the set. And you're like, well, I already knew 1 was in the set, so that's silly, right? So that's the idea that it's in both, and both just gets listed once. All right, last but not least, we have an addition rule for counting. We know that the number of things that are in the union of two sets is equal to the number of things that's in the first set plus the number of things that's in the second set minus the number of things that's in their intersection. And I think it's much easier to see this from a picture. So here's A, here's B, right? So the number of things in A, you're just going to count up everything that's in A, right? So you're going to count up how many elements are in set A. And there might be some things in here, right? There might be some elements in here. We don't know how many. And then B, if we count up all the things in B, we're counting everything that's in B. But look what just happened, including all the stuff in there. Didn't we end up counting that little football twice, right? So when we end up counting that football twice, all of these things end up getting counted twice, and so that's why we have to subtract them away. So yellow, right? This was yellow. This was green. And then the intersection ended up looking black, right? I'll put both colors on it so it looks the same, right? Oh, now we can't even read it. That was stupid. But you get the idea. This is the intersection of A and B. So if you count up everything in A, you're going to count everything in that little middle piece. And then if you count up everything in B, you're going to end up counting that little middle piece again. So you have to then subtract how many things were in that middle piece because they got counted twice, and if you subtract them away, they now have only been counted once, and now you've counted up everything that's in A and B put together. This is a rule that will help us later on when we get to probability. All right, that's everything we need to know about Venn diagrams. But just as a side note, just in case you come across it, all right, here's a Venn diagram with 3 things, A, B, and C. And we can actually expand this counting rule out for 3 things. We can count up everything in A, everything in B, everything in C. Then we subtract everything that's in A and C, everything that's in B and C, and everything that's in B and A, because these things have all been counted numerous times. And by subtracting them away, we've subtracted away all those numerous things. But we've actually subtracted this thing away too many times, right? We subtracted away once, twice, 3 times. Now it's never been counted, right? Because it was counted once when we did A, twice when we did B, 3 times when we did C. We take this away, we take this away, we take this away, and now that one's missing. So then we just add it back, right? So you do A plus B plus C, subtract each one of their intersections, right? So take away A and B, take away A and C, and take away B and C, and then add back the 3-way intersection, the A, B, and C, that little middle triangular piece. And then that gives you everything in all 3. And you're like, your head's probably spinning at this point. Don't worry, I don't think we see any of these in our class, but just in case you were curious, it can be expanded and it can go out and out even further and further.